Okay, so for our next example about Taylor polynomials, we're actually going to look at a Maclaurin polynomial. So remember when you see the word Maclaurin, that's just going to tell you that your C value is 0. So we want the fifth degree polynomial for sine of x. So again, we're going to make that little chart of derivatives and values. So I have f of x is sine of x. I'm just going to go through and do my 5 derivatives first. Right, and sine is great because it's got, I'm sorry, my dog is crying in the background. He needs attention. All right, because they just keep cycling between cosine and sine, just changing the symbols in front, like positive and negative. So that's positive sine of x, and then I got my fifth degree. Okay. All right, and then going through and finding my value for each of these at 0, which is nice because that's a unit circle value. So we have, that's going to be 0. It's going to give me 1. It's going to be negative 1. Hopefully you can kind of see what's happening here is, right, all of our even powers of our derivatives, and you can kind of think of the actual function being like the 0 degree derivative of the function, right? Those are all going away. Those are 0. Hang on, sorry, my dogs are starting to fight. We're going to try and separate that while I continue recording this. So, right, we got our fifth degree Maclaurin polynomial. Some people use an M for Maclaurin polynomials, so we'll go ahead and use an M. So we have fifth degree Maclaurin is going to be our function value, so 0. We're going to write out all of the terms here, plus our first derivative times x minus 0, which is just x, plus 0 over 2 factorial times x squared. And then it's going to be plus our third derivative, which is going to be negative 1 over 3 factorial times x cubed, plus 0 over 4 factorial times x to the 4th, plus 1 over 5 factorial times x to the 5th. Okay, but we're going to rewrite that, of course, to get rid of all of those zeros. So we're going to end up getting x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th. Hopefully that looks familiar for those of you who watched the first video from that initial kind of calculator exploration. And if we want, we could actually simplify that. Right, we could write out what those values are equal to for the factorials, but you don't have to. I actually usually prefer to just leave them with the factorials in the bottom because a lot of times you can kind of see the pattern that's happening each time. Okay, so we're going to use that to find P5 of 1.4, which is also, since I named it with M this time, 1.4. So I'm going to go ahead and use my calculator. So I'm going to pull this out. Right, I'm approximating 1.4. So I got 1.4 minus 1/6 of 1.4 cubed plus 120 over times 1.4 to the 5th power. So quickly just typing that in as fast as I can. I get that that is approximately 0.987. And the actual value of f of 1.4, really that's the sine of 1.4. Again, remember, if you haven't used your calculator in a little bit, check that you're in radian mode first. Type in sine of 1.4. And our calculators to 3 decimal places is 0.985. So the error in our approximation, which is the absolute value of the actual value minus the polynomial approximation, right? It's just the difference between the two values. Our error here, right, if we subtract those two, is going to be 0.02. Right, so not a bad approximation. So we're going to do the same thing. Now we're going to use that same approximation for 2.1. So all I'm going to do on my calculator is I'm going to scroll back up and kind of copy and paste and replace all of those 1.4s with 2.1s. If you're ever doing a problem like this and you can tell that you're going to use the same equation multiple times, right, just throw that in your y equals so that way you don't have to do anything other than go and type it in using your vars. So this is going to give me 0.897 if I round it to 3 decimal places. And then my actual sign value of 2.1 is 0.863. So my error here, right, this is my error when I subtract them and take the absolute value. I'm going to get 0.034. I actually just like copy and pasted the full decimals to subtract them so I could get as accurate of an error number as possible. So we can see that our error, the error for the second one, right, error for 2.1 is higher. Right, and remember that these are approximations centered around a specific value. So as we get further and further away from our center, our error value is going to go up and up, right? So we're going to get a larger error here if we use our approximation for 2.7, since 2.7 is further away. From c equaling 0, right? So we're centering this approximation around x equaling 0, c equaling 0. So really close to 0, our approximations are going to be very tight, but as we move further away, we're going to get larger and larger errors. Think about those initial graphs that we looked at as we kept adding on each successive term, right? The polynomial was more and more on top of the sine function as we added more terms. So really close to the x equaling 0 value, we're going to be really close, but as we move further and further away, our polynomials aren't going to completely follow that sine curve, so our approximations are going to be worse. Okay, we're going to do one more example problem in here before we close out this video. So we're going to use a third degree Taylor approximation for the function e to the x, so getting a new function here near x equaling 0, to find the limit below. Right, so if we were to evaluate this, we could do L'Hopital's rule, right? We can find out this limit initially before we even do this. So, right, using L'Hopital's, right, we know that the limit as x approaches 0 of the numerator is 0, right? The limit as x approaches 0 of the denominator is equal to 0, right? We get an indeterminate form, so, right, by L'Hopital's rule, we get that this is equal to the limit as x approaches 0 of the derivative of the top, which is e to the x, over the denominator, which is just going to be equal to 1/2. So we're going to use Taylor polynomial approximations to show that we're going to get the same thing. So this is a third degree Taylor approximation, but it's using near x equaling 0. So this is our c equaling 0 value. So this is actually a Maclaurin polynomial, right? So you'll get them referred to both ways. If it just says Maclaurin, it's not going to have to tell you that it's going to be c equaling 0, but they might tell you that it's a Taylor with c equaling 0. That's totally fine. So again, I'm going to go through and find my function value and all of those derivatives that I need. So third degree means I need 3 derivatives. The beautiful thing about e to the x here is that they're all the same, so it's just writing it out. Right, and then if I'm evaluating them at 0, they're all going to equal 1. So this is really nice. Right, so if I go ahead and make my third degree polynomial, you can use whatever letter you want, P, M, T, choose whatever you want. So, right, I take my function value of 1, and then I'm going to add to my first derivative, times x to the first power, right, because my c value is 0, so I don't have to do the quantity thing, plus my second derivative value over 2 factorial times x squared, plus my third degree value over 3 factorial times x cubed. right? And if you want, you could say that that's 1 plus x plus 1 half x squared plus 1 6x cubed, right? You could simplify those factorials. So now when we're finding the limit, as x approaches 0, of e to the x minus 1 over 2x, we can say, well, that's going to be approximately the same as the limit as x approaches 0 of, and we're just going to replace e to the x with its Taylor polynomial approximation, right? This is approximately e to the x. So we're going to replace that there. So we've got 1 plus x plus 1 half x squared plus 1 6x cubed, and then we still have that minus 1. And then it's all over 2 to the x. So this is going to equal the limit as x approaches 0. So our 1 and negative 1 is going to cancel out. And then I can actually divide the top and the bottom by x to simplify it. So we're going to get 1 plus 1 half x plus 1 6th x squared all over 2. So the denominator is going to 2, and then as x goes to 0, this goes to 0, and this goes to 0. So our overall limit still equals 1 half, right? So just an example of the fact